we're going to work through 3 different examples of thin lens problems. The 3 different cases for thin lenses that are listed on your equation sheet. So you have an example of all 3 of them, okay? So our first case is when we have a converging lens, so a lens that looks like this shape, okay? And our object is a distance away from our lens that's greater than the focal length of the lens. So here's my midline of my experiment going through the midpoint of my lens, and this is my lens. This is the midpoint line of my lens. So didn't do a great job of drawing it, but here we are. Okay, so we're also going to do the ray tracing too. And so for this problem, we're going to have a focal length of 10 centimeters for our lens, and our object is going to be setting a distance of 30 centimeters to the left of our lens. So my object, I'm going to draw it over here. I'm going to draw my object as sort of this little arrow right here, okay? And so we have to figure out the distance that the image is from the lens. We have to determine whether this is real or virtual. And then we got to figure out what is the magnification of our lens. Okay, so the first thing I've got to do, okay, so the focal length was 10 centimeters. Here's the focal length, the distance of 10 centimeters away from my lens. I'm marking that as F because that's what we're calling the focal length of the lens. And then I've got twice the focal length, which would be 20 centimeters, 3 times the focal length, 30 centimeters, which is where my object is sitting. Okay, and we've got to figure out where is the image located with respect to the lens. To do that, we'll use the thin lens equation. But first, let's do the ray tracing to get an idea of where is this image of this object going to appear when the light is refracted through the lens. Our first rule for ray tracing for converging lenses here, a ray entering a converging lens parallel to the axis passes through the focal point of the lens on the other side. Okay, so what does that mean? I've got to go parallel to the axis. Okay. There. And then I have to pass through the focal point on the other side. So I cross the midpoint of my lens and through the focal point on the other side. So my drawings are going to be a little bit off. They're not going to be as good as what you could do with a ruler on your own at home. Okay, so this is for my first ray. My second ray, a ray passing through the center does not change direction. So my ray going through the center of my lens does not get refracted at all. Let's draw that in. We're not going to get refracted. We're going to go straight through. Okay? So this is my second ray. My third ray, a ray entering a converging lens through its front focal point exits parallel to the axis. So my third one, I'm going to go through the focal point here. And then I'm going to go parallel to the axis after I go through the center of the lens, okay? Parallel to the axis. And I didn't quite get those 3 rays to converge, but I got close. So right around here is where my 3 rays converge. So right around here is where the tip of my little object is going to be. So the tip of my little object is going to be here. The bottom part of my little object is going to touch the center point. And so actually my object, it looks like it's going to be on the other side of the lens. It's going to be upside down, so it's going to be inverted. And it looks like it's going to be smaller than the original image. Okay, well, let's see if the math works out. Okay, so in order to use the thin lens equation to figure out what is the distance that the image is from the lens, let's do that. So our thin lens equation, we have 1 over the focal length is equal to 1 over the distance to the object from the lens plus 1 over the distance to the image from the lens. So we're solving for DI. So I'm going to subtract 1 over DO to the other side, okay? And if I do that, then I have 1 over DI equals, I'm going to subtract this term to the other side, 1 over F minus 1 over DO, okay? So what I'm going to do to make it a little bit easier for us, let's go ahead and see, we'll go ahead and plug in the numbers here. So 1 over F is 10 centimeters minus 1 over DO, the distance the object is from the lens, is 30 centimeters. Okay, so in my calculator, I'm going to say 1 divided by 10, parentheses, minus 1 divided by 30, parentheses. So 1 over DI is equal to 6.67 times 10 to the minus 2 inverse centimeters, 1 over centimeters, because we've got 1 over the unit of length. So that's 1 over DI is equal to this number. To get DI, we have to take the reciprocal of both sides. Okay, so if we do 1 divided by 1 over DI, we get back DI. So DI is equal to 1 divided by, so the reciprocal of this, 6.67 times 10 to the minus 2 inverse centimeters. So now the distance to my image is going to be the inverse of this number, the inverse of 1, so I'll do 1 over 6.67 times 10 to the minus 2, and then that gives me 15 centimeters. So 1 over an inverse centimeter is going to give me back the centimeter. So the distance my image is away from the lens is 15 centimeters. And if this number is positive, that means that my image is on the opposite side of the lens from my object. So if this was my object, my image is over here. And so I'm seeing that it's at 15 centimeters, and I drew my ray tracing here. So it looks like we did an okay job. My image is going to be on a little bit outside of the focal length. The focal length was 10 centimeters. Okay, so my image sketch from the ray tracing turns out to be just a little bit further outside of the focal length of this lens. So we did an okay job there with doing the ray tracing. So we can verify ourselves in a couple of different ways here. So we have A, 15 centimeters. Is it real or virtual? Well, for a lens, if your image is on the opposite side of the lens from your object, then you have a real image. So we're real. And then our magnification. So the magnification, there's a couple of ways you can find it, but one of the ways you can find it is by taking minus DI over DO, minus the distance to the image over the distance to the object. So we've got minus, distance to the image was 15 centimeters, distance to the object from the lens was 30 centimeters, so this is minus 0.5 is the magnification. The minus sign means that it's inverted, that our image is upside down. And then the 0.5 means that our image is actually half as large as our object. So our image actually gets smaller when the light gets refracted through this lens. Okay, so this is how you could analyze and solve a problem where we have a converging lens where our object is located at a distance away from the lens greater than the focal length. Now our second case for the thin lens equation, we've got a converging lens, and this time our object is going to be located at a distance away from the lens that's less than the focal length of the lens. Okay, So in this problem, we're going to have the focal length of our lens is still 20 centimeters. The distance that our object is away from the lens is 5 centimeters. And we have to figure out where's the image located, is it real or virtual, and what's the magnification. First, let's start with the ray tracing. So let's see, if this is my focal length of 10 centimeters, half of that is where my object is sitting. So I'm going to put it right here, okay? So now just to let you know that the shape of my lens here is highly exaggerated, right? In real life, they're going to be really, really, really skinny. This is just sort of a cartoon drawing, okay? So here's my image. I'm going to call it I, all right? And it's 5 centimeters away from the midpoint of the lens. Let's do that ray tracing. So the ray tracing is going to feel a little bit different. The rules are essentially the same, but it's going to feel a little bit different since our object is closer in to the lens, okay? We still have the ray traveling parallel to the axis, and it passes through the focal point of the lens on the other side. Then we're going to have our ray coming parallel to the lens right here, and then that ray is going to pass through the rear focal point, okay? There. Then we have the extension of this ray that goes up. I'm going to put it in a dotted line here in this direction, okay? Now, so that's our first ray. For our second ray, the ray that travels through the midpoint of our lens is not refracted. So let's do that one. It's going to travel through the midpoint here. Okay, and we also have this little extension that goes back here. And where these two intersect is where my image is going to appear. And actually I labeled this one right here incorrectly. This first arrow that I drew here was not the image, that's the object, okay? That's the object that the light is leaving from that object being refracted by this lens. And this is the image that we end up with, okay? So whenever we have our object inside the focal length of my lens, we actually get an image that's on the same side of the lens as the object, okay? And when the image is on the same side as the object, we call that a virtual image. So I already know that this is going to be a virtual image, but we'll show it to you also through the math as well. Now we'll use our thin lens equation in order to figure out what is the distance that this image is away from the lens. Okay, so we're trying to find d sub I, so we're going to solve this for d sub I like we did before. I'm going to subtract this term over to the other side. 1 over di equals 1 over f minus 1 over do. So this is equal to 1 over f was 10 centimeters minus 1 over do was 5 centimeters. So again, when you're typing it into your calculator, you're going to put parentheses around these bits. 1 over 10 parentheses minus 1 over 5 parentheses. 1 over di will equal minus 0.1 inverse centimeters. So we take the inverse of both sides in order to get di. So di is equal to the inverse 1 over negative 0.1, negative 1 over negative 0.1, and then that's minus 10 centimeters. Okay, so my image should appear, the minus sign means that my image is going to appear on the same side of the lens as my object. So that minus sign means that my image is going to be 10 centimeters away from the lens on the same side as the object. And didn't quite get the geometry just right here. My image should appear right at the focal length then, because the focal length of my lens was 10 centimeters. In my ray tracing, I got it just a little bit outside of there. But actually, looks like I drew the focal length a little bit too close to the midpoint of the lens here anyway. Okay, so that is how we could do this example for case 2. It's virtual because the image is on the same side of the lens as the object. It's upright. It's not inverted. It's not flipped. The magnification is minus DI over DO. This can be minus negative 10 centimeters over DO is 5 centimeters. So that negative times a negative is a positive. So we've got 10 over 5. So our magnification is plus 2. So the positive sign means that we're upright, our image is upright, same orientation as the object. And this means that my image should be twice as large as my object. And it looks pretty good here. So if you're doing like a super precise job and actually using a ruler to really measure out everything, if you're actually measuring out everything properly when you're doing the ray tracing, you can actually go in there with your ruler and measure to check, was the height of my object that I drew half the size of the height of my image, or is the height of my image twice the size of the height of my object? Finally, our last case, case 3, for diverging lenses. Now, diverging lenses always have a virtual image. So that means that the image always appears on the same side as the object. So we are going to know what that is. It's always the case. Okay. Now, also a diverging lens has a negative focal length. So we're going to have a diverging lens with a focal length of 10 centimeters, but we put a minus sign on it since it's a diverging lens. And we're going to put our object at 30 centimeters away from the lens. So my object, I'm going to put way out here. And we're still going to find the distance that the image is from the lens and the magnification. And then the first thing we're going to do is the ray tracing. So the ray tracing rules are a little bit different for diverging lenses. A ray entering a diverging lens parallel to its axis seems to come from the focal point F. Okay. So we're going to have a ray traveling parallel to the axis. There. And it's going to seem to appear to come from our focal point F. So we're going to diverge over here, but we're also going to draw the sort of extension that goes through the focal point here. Okay, so that's ray 1. Ray 2, that our ray passing through the center does not change direction. Okay, so it doesn't get refracted. So then this ray is going to go through the center. Like so. Ray 2. And then my third ray for the diverging lens. A ray that enters a diverging lens by heading toward the focal point on the opposite side exits parallel to the axis. So we're going to head toward the focal point. Pass it through the focal point like this. Okay. But we're going to exit parallel to the axis over here. And then we're going to draw a little line that extends backward this way. Okay. So we diverge over here. My image is going to appear right here where these sort of 3 lines are going to kind of come together to one point. So if this was my object, my image is over here. Okay, so it's hard to see, but my image is going to appear upright on the same side as the object, so it's a virtual image, and it looks like it's going to be smaller than our object. So we're going to do the math in order to check ourselves. Okay, in order to find the distance that the image is from the lens, we're going to use our thin lens equation. We're going to solve this for 1 over di. 1 over di equals 1 over f minus 1 over do. And that's going to equal 1 over negative 10 centimeters, because remember our focal length is negative for a diverging lens, minus 1 over distance to the object, which was 30 centimeters. Okay, so in your calculator you're going to do minus 1 over 10 minus 1 over 30. So 1 over di is going to equal negative 1.33 times 10 to the minus 1 inverse centimeters. So we take the inverse of both sides, so 1 over this number gives me di. The di is going to equal minus 7.5 centimeters. So the minus sign means that our image is on the same side as the object. So our image is going to be right here on the same side as the object. The distance away will be 7.5 centimeters. So I put my point here to represent the distance that is the focal length. Our focal length was minus 10 centimeters or 10 centimeters. So my image should appear closer to my lens than my focal length than it does right here with my ray tracing. Okay. Then we already talked about how it's virtual, it's upright, and you can tell that its magnification is going to be smaller than 1. So magnification equals minus di over do. So it's going to be minus negative 7.5 centimeters over 30 centimeters. The centimeters cancel. So we've got a minus times a negative, that gives us a positive value. We've got 7.5 divided by 30. So this gives us a magnification of positive 2.5. So the positive means that it's upright. The 2.5, well, that means that it's a quarter or a fourth the size. The image is a fourth the size of the original object. So now you have 3 examples for the 3 different cases we can have for our thin lens problems using our thin lens equation, depending on whether or not we have a converging or diverging lens and where our object is compared to the size of the focal length.